Hi everyone. So in this video, we are going to see one of the most elegant theorem in DFS, which is DFS parenthesis theorem. So why I'm telling this that this is most elegant, because this is very easy theorem. Let me just quickly go over the CLRS or the Corman screenshot that I have taken. So what they are trying to say is that in DFS you consider discovery time and final times or the finish time. So D means discovery time and F means finish times. So let me first tell you that this is very much analogous to balanced pair parenthesis. How? Let me just first tell you what is balanced pair parenthesis. See, in balanced pair parenthesis, what does happen? I say that this pair, let's take any pair of parentheses, this pair is balanced and this is a valid pair parenthesis. Why? Because this is a start of some parenthesis and this is a closing parenthesis. In between you are having a start end, right? So this one is valid. Similarly, if I ask you whether this is valid or not, then just tell me whether this is valid or not. This is not valid, right? Why? Because this is a start, or this is an opening parenthesis and this is a closing parenthesis, and in between you are not having a balanced parenthesis, you are having opening parenthesis only. So this is not balanced and this is balanced. Similarly, just tell me whether this is balanced or not. This parenthesis, obviously this parenthesis is also balanced, because here it is balanced, it is balanced. So this particular parenthesis is also balanced. Now just tell me whether this parenthesis is balanced or not. Just let me take some last example. Just tell me whether this parenthesis is balanced or not. Obviously this is also balanced, because this is a start and this is end, that is why this is also balanced. So as you see, these are the three parenthesis pairs which are balanced and this is not balanced. Now the exactly same analogy that they have taken in Corman book, and they have said like we can map DFS intervals just like balanced pair parenthesis. So what they are saying, that whenever you are starting some DFS on any node, suppose that this is a node U and this node U exploration is start, and then let's suppose this is the time frame and this is start of U, and let's suppose this is the end of U, and in between something is happening. So for example, let me take a concrete example. Let's suppose this is U and you are probably going to P, and then let's suppose you are going to Q, and let's suppose you are going to V. So what's going to happen once you start this U? Then what are the next thing that you are going to do? Let's suppose this is the graph and I am running the DFS on U. So you will start at U, you will go to P, which means then you will start P, and then you will start Q, and then what you will do? Then you will say that Q is finished, so you will go back to P, and then you will say that P is also finished because all of its adjacents are finished. So you will say end of P. And now you will go to U and you will say that okay, till now this is not end of U, so I will do the end later. So you will say that okay, end of P is there, and then you will go back to U. You will say that okay, now let me start V, and then you will say that V is also finished, let me end V, and then once everything is finished you will say that end U. This is how you will be saying that this is start and end, isn't it? Now let me just map this whole scenario to our parenthesis. So let's suppose that start of U is this kind of parenthesis and end of U is this parenthesis. Let's take start of P as this parenthesis, end of, or maybe let me just probably use this parenthesis, and end of P is here, which is, let's suppose, this parenthesis. And let's say that start of Q is this parenthesis and end of Q, okay, I think I have not written end of Q, so end of Q just after immediately start of Q, right? So end of Q will be this. Let me just make some space, because otherwise it will be little messy. So let me probably go to the next page, or maybe let me just make some space here only. Okay, so let's say that after so after this after the start of Q, you will be having end of Q immediately, which means this is start of Q. Let's suppose this is end of Q. Now you are having start of v. So let's say that start of v is this parenthesis, maybe this parenthesis, this is start of v, and then you are having end of v. Now end of u is this parenthesis. Okay, everything is fine, which means I do have start of u parenthesis, end of u parenthesis. Basically I have mapped everything to just parenthesis. Now you just notice one thing, that this is one parenthesis pair, right? This is start of u and end of u is one kind of parenthesis, and in between there are balanced parentheses. See, this is start of u and this is end of u. Now let's assume that this is one kind of parenthesis, and in between this is start of p and this is end of p, this is balanced. This is start of q, this is end of q, this is balanced. This is start of v, let me use some other color probably. This is start of v, this is end of p. So this is how I am saying that, see, this complete thing is balanced pair parenthesis. You can easily verify it. This is very easily verifiable that it is a balanced pair parenthesis. So what does this theorem says is that whatever you do in DFS, okay, so just make this as a start and end and just map it to a balanced pair parenthesis or a pair of parentheses, it will be automatically balanced. Which means it is trying to say that let's suppose start of s is here and end of s is here, which means let's suppose this is the time 1 that s is getting started, and this is the time 10 when s is getting ended. So let me just represent this with this pair of parentheses, start of s and end of s. And in between, let's suppose z is getting started and z is getting ended. So z start, let's say this, z end, let's say this, and then y start and y end, and then x start, x end, and then w start, w end. So this whole thing, like this DFS traversal whole thing can be mapped with the balanced pair parenthesis like that. Now why it is useful, you will get to know in just a minute of time. Okay, this theorem is extremely useful and you will be able to solve questions just a blink of seconds, blink of eyes. And just see this, see here, this is start of t and this is end of t. In between you are having start of v, end of v, start of u, end of u. Right? Now just let me just read out this theorem. It is saying that in any depth of a search of a directed or undirected graph G for any two vertices u and v, exactly one of the situation will hold. First is saying the intervals which is start of u and end of u. This is start of u and this is end of u. Let's suppose this is one interval, and start of d and end of d are completely disjoint. So they are saying that there will be three cases. First case could be that start of u, end of u, and start of v, end of v are completely disjoint, which means if you just map this with a pair of parentheses, then there will be this pair of parentheses. Okay, this is just one case. Another case could be, let me take it case 2. Another case could be the interval which is start of u and finish of u is contained entirely within this interval, which means that you take interval of v, this is completely interval of v, and in this interval that u interval is entirely contained, which means that u interval will be something like this. Which means if you try to map this with the balanced pair parenthesis, then this is start of v, this is end of v, and here you have start of u and end of u, which means you are having a balanced pair parenthesis. So these are the two situations, and the third situation is saying that this is exactly same as second situation, which is saying that u this u interval can be superset of v interval, or v interval can be entirely contained. Just see, the interval v is contained entirely within the interval u, which means this interval v is contained entirely within the interval u. So there are three situations. Either they are completely disjoint, or one is another, one is in between another. And what is not possible? So these are the possibilities. Let me just tell you what is not possible is this. See, just see the possibility which is not possible, something like this. So if I ask you, is this possible, which means this is start of u, this is end, this is start of u, end of v, like that, is this possible? If I ask you, is this possible, then you will say no, this is not possible, no. Similarly, if I ask you, is this possible, which means if I ask you something like this, okay, maybe let me just reverse the role u and b, then you will say it is also not possible. So these kind of intervals are not possible. Neither this is possible nor this is possible, and these intervals are possible. Similarly, if I ask you, is this possible? Is this possible? Then obviously this is possible. In fact, this is just a first case. So these kind of intervals are possible. These three intervals, these kind of intervals are not possible. Not possible. So let me write not possible. Similarly, it is also not possible. Now, what is use of this is that you can make the entirely DFS tree just by having these times. So let me just go to the question directly and let me show you how we can do it. See, this start time and finish time, I will be visualizing this just an interval like this. Let's directly go to the question. So in this question, I have taken this question from some university, and they have 5 questions, and they have given these 8 vertices and their start time and finish time. So let's just do one thing. Let's make the DFT out of it, which means I will be using this start time and finish time, and I will be making the depth first tree using that. How? Let me just show you. See, the vertex 1 is having 4. Okay, let me see. Okay, vertex 7 is having 1 as start time. So I will say that vertex 7 is getting started here, and vertex 7 is probably getting finished here. Maybe let me make a little longer. So vertex 7 is finished here. So this is 1, this is 10. Right? So vertex 7 is finished. Let me just write it 7. Okay. Now let's just see that what else. 6 is getting started at this point and getting finished at 9. Okay, and getting finished at 9, which means here. So this is 6 done, and then 5 is 3 to 6. So this is 2 to 9. 5 is 3 to 6. So maybe from here to probably here 3 to 6. Okay, 3 to 6. Then let me just make it from here to here. So this is 3, this is 6, and this is 5. Now let's just see that do we have 4? Yeah. So vertex 1 from 4 to 5. So this is from 4 to 5. This is vertex 1, right? This is from 4 to 5, and this is also done. Then vertex 2 from 7 to 8. So which means vertex 2 will be from here 7 to 8. This is vertex 2 from 7 to 8, and then you have vertex 3 that is from 12 to 13. Okay, so which means that vertex 3 will be here after this interval. Let me make one more interval. So vertex 3 will be from 12 to 13, which means from here to here. This is 12, this is 13. Okay, in between you have 11 also. So let me just make this little, let me just zoom in of this, or maybe zoom out, and then let me just accommodate other vertices. So here you have 12. Okay, after 10 you have 11, which is vertex 8. So from 11 to you have 16. This is vertex 8. That is 11 to 16. This is vertex 8. So you are saying that okay, vertex 8 is also done. Let me write vertex 8, which is also done. Then after 11 you have 12, which is 3, and that is from 12 to 13. So which means you have 12 to 13. So this is 12, this is 13, this is vertex 3. Okay, this is also done. Then you have 14 to 15, and that is vertex 4. Okay, so you have 14 to, this is 13, then you have 14 to 15, which is vertex 4, right? Now this is also done. So all of the vertices are done. Now I have this this interval chart. What can I do with this interval chart? I can immediately make a tree. How? I know that this is getting started first and then this. So it means that this have to be like parent, or the ancestor of these nodes, which means 7 will come like this, and after that 6 will come, and after that 5 will come, and also this interval is disjoint. So after 6, see 7 inside the 7, 6 will come, and then 6 is having two intervals. One is this, another is this, right? 6 is having 2 intervals, which means 5 and 2. So 6 will be having 5 and 2, and then 5 is having just 1, which is this. So you can make a depth first tree just by looking at the interval. This is the beauty of this algorithm or this theorem. What you can do, you can basically have an interval chart, and using that you can make a depth first tree, right? And just make a depth first tree out of this. See, this is vertex 8, and then you will be having two of its children, which are 3 and 4. So what you can do, given these start time and finish times, you can map these start time and finish time to these trees, or you can do vice versa, which means given these trees you can also have some start time and finish time. You can make this interval chart. I hope you got it, right? So what we need to do, we just need to apply this theorem. This theorem is saying that, see here, let me just read out this theorem. This theorem is saying that for any two vertices u and v, one of these will hold. Okay, and what you can do using this theorem, basically you can say that if that s, the interval of z is entirely contained in interval of s. Okay, let me write here, if interval of z is entirely contained in interval of s, then z is ancestor of, sorry, s is ancestor of z. S is ancestor of z. Okay, this is the inference that we are taking from this theorem, and it can be proved also, but we do not need to prove it. So which means that if z interval is entirely contained in s, then you can say that z is the s is the ancestor of z, and then you can make a DFT very easily. Okay, so now you can answer all of this question, what are the descendant and ancestor of vertex 6, like that. You can say that, okay, for vertex 6 the descendant are 5, 1 and 2 and ancestor is 7. So I think, yeah, this is the solution that that is given by the university also. So I have pasted that solution also, right? So these are the answers that they see, 7 and 1 to 5, and these are the answers of all of this question. You can try this question. These are not hard questions, just easy questions. Just try out all of this these questions, these 1, 2, 3, 4, 5 questions, and once you make a tree, then these questions will be very, very trivial. Now let's move to other questions. See this question. Here, this question was asked in CMI, some quiz, I think. Okay, and then they are asking the same thing, that given the following data about the DFS on the directed graph, reconstruct the DFS tree or the depth first tree, DFT or DFS tree. So entry and exit is just a start time and finish time. This is just a start and this is just a finish. So let's try doing it, or you can do it probably, right? So they are saying that vertex A is having a start time of 2 and finish time of 13. That is okay. Vertex B is having a start time of 1. So maybe B will be coming like this, right? This will be 1 and 14. So you can try out this question, and the answer is on the next page. Just try out this question and you can see the answer on the next page. This is just a easy question. Now suppose that I do have some situation where the tree is given. Probably let's say that some tree is given to me, and then they are asking, let's suppose this is one tree they are giving to me. So let's suppose some forest is given to me, some DFS forest, where they are asking, let's suppose this is F to G maybe, and then H, and then let's suppose this is I, and let's suppose this is J to K, and then maybe L, and then they are asking what are the start time and finish times. So what you will be doing, you will be making different like intervals, which means you cannot tell the exact time because it is just relative. You do not need to even tell the exact time, but let's suppose the question is like this: given this forest, okay, given this forest or DFS forest, draw intervals. Then can you do it? I think you can do it easily. You will say that B is having the largest start time. I mean, B will be starting first. So let me probably go to the next page, and then let me just solve this question. So let me just minimize this, and let me try solving this question. You will say that B is having the highest start time and finish time. B will be something like this, and then A will be after it. A will be this is B, this is A, and then D. Okay, let's suppose this is what was that? This is E, this is C. Okay, this is E. Now inside this D only there will be E and C. So inside this A there will be D, and inside this D only there will be E and there will be C. So based on that, you can just number it anything, maybe from 1 to 10, something like that. You can number it anything, does not matter. Okay, but you can make an interval chart like this. Similarly, for this you will be making an interval chart which is F, something like this, and this is F. Then inside this F, this is G, this is H, and then inside this G you have I. Like this you can make an interval chart. Similarly, you can make an interval chart for this. You will say this is J, this is K, this is L, something like that. Now, if this is a start, like if this is 1, this is 10, something like that, or this should be 1, that does not matter. I mean, you do not know whether this B has been started first, or F has been started first, or J has been started first. But you know that B has been started, and after that only A has been started, and after that only D has been started, and after that only E has been started. And once E is finished, then okay, in between E and C also you do not exactly know that whether E has been finished first or C has been finished first, but let's not worry about it. Let's say that once E is finished, then C has been started, something like that. But you, at least you know that once D is finished, then only A can finish, and then only B can finish, right? So obviously, like suppose this is the tree that you have, and if I say that this is a tree, then obviously in this tree A has to finish, then only B can finish. See, if you have something like that, B, A, okay, this is the tree that you have, B, A, and then D. This is the DFS tree that you have. Now, obviously in this DFS tree, if that is the DFS tree that you are getting, then final DFS tree, I'm not saying this is the graph, I'm saying this is a DFS tree or the DFS forest that you have. And in this, you must be having something like this only when this A has been finished, then only you must be finishing B. How can A be finished and B is a parent of this and B is not yet finished? Sorry, how can B is finished and A is not yet finished? It is not possible, right? So if this is DFS, then DFS forest or DFS tree, then it is 100% sure that A is finished and then B is finished, right? You cannot say that B is finished, like we cannot have B finish then A finish. How can B be finished first? See, this A is a child of this, so how can B be finished first? B has to finish once all of the childs are finished, all of the children are finished. So let's suppose this is DFS tree. Then I will say that we cannot have a situation where B finish then A finish. We cannot have, which means that A or A has to finish. Let me write like this: A has to finish before B finishes, obviously, right? A has to finish before B finishes. So anyway, these kind of inference you can make, or otherwise very simply you can just apply the theorem. You can just make the interval chart, and then you just say that okay, A has to finish once before the B finishes. You can make these kind of statements after the interval chart, right? Okay, let me try solving more questions. Let's see what this question is asking. V is a descendant of U, okay, which means V is here and U is here in a DFS tree, if and only if. So they are saying in a DFS tree. So this is DFS tree. They are talking about DFS tree. They are not talking about the graph. They are saying the DFS tree. If and only if a start of U, which means a start of U, and this is finish of U, in the finish of U, this is a start of U and finish of U, in between a start of V, so this is U, and a start of V and finish of V. Yes, that is true. If you have DFS tree like this, then these two are analogous basically. If you have like this DFS tree, then you can make this. If you have this, then you can make this. This is if and only if. Okay. So if they are asking true or false, then you will say this is true. You should be able to solve these kind of questions very, very easily. See, these two are very much interchangeable. I mean, you have this, then you can make these intervals. If you have these intervals like this, if you have these intervals, let's suppose in this question that we did, if you have these intervals, then you can also make the trees. If you have interval, you can make the tree. If you have the tree, you can make the interval. So you can do whatever you want to do. Which means if you if you want to go from interval to tree or tree to interval, it is your choice. So for this question, I will say this is true. Okay. Or let me just copy this, and if you want, you can try solving this. So let me just remove this, so that if you want to try, then you can try it out. I have taken this question from one university, and the link is below, but you do not need to go to that link, because otherwise it will just your waste of time, because I have already taken the relevant questions from wherever I was finding. Okay. If that link is containing multiple questions, then I must have taken the multiple questions. Okay. Let's solve this GATE question, which is GATE 2006 questions. They are saying consider the depth first search of undirected graph. They are giving the undirected graph with 3 vertices P, Q and R. and let discovery time du, so start time and finish time they are giving. So they are saying that this is start time, this is finish time, which means P start time is 5, and after that at 12 Q is getting finished. So this is P, and in between 6 and 10 this is Q, and then 14. Okay, 14 means this is not in this interval, which means this is coming maybe on the side, which means you will be having this R somewhere here from 14 to 18. This is R, right? And now what they are asking, okay, which one of the following is true? Now can you make the tree? Obviously we can make a tree. So if you want to make a tree, then tree will look like this. So they are saying there is only one connected component. No, there are, see, if you are getting multiple, see, they are saying undirected graph. In undirected graph, if you are getting 4h, then what does this mean? The graph must be disconnected, right? In undirected graph, you cannot get a forest if a graph is connected. If a graph is connected, then you obviously you will be reaching from somewhere to somewhere. If you are getting these two trees in the DFS, it means the graph must be disconnected. And there are two components. One component in the graph is this, another component is this. So there are two components, and PR are connected. No, PR are not connected. There are two components, and Q and R are connected. No, there are two components. PR, yeah, D is the answer. See, the moment you make this out of this interval, the moment you make this forest, this question is extremely obvious using this parenthesis theorem. So this parenthesis theorem will basically just give you the confidence that how to deal with this start time and finish time. Okay, and that is why I say that this is very elegant, very easy, and very useful theorem. Now let's solve this question. Which of the following is not possible? They are saying not possible. So first condition is saying start of U and finish of U in between, okay, start of V and finish of V. So what you can do, you can try this question and then just see the solution later. Okay, just pause this video and then see the solution after that. Okay, let me try solving it. So is this possible? Yes, obviously this is possible. Why? Because this is what parenthesis theorem says. And then similarly they are saying start of U and then finish of U, which means U is here, and then after that V start, V finish. Yes, this is also very much possible. Let's see this. Start of U and then start of V, okay, and then finish of U, and in this interval start and end. Okay, so they are saying something like this. Is this possible? Obviously this is not possible, and that's what parenthesis theorem says. So that is why you will say this is not possible. And let's just check this last option where they are saying start of V and then finish of V, which means here this is V and inside this there is U. Yeah, this is also possible. So A, B and D are possible, but C is not possible. This is easy question, you should be able to do it. Okay. So from this theorem, what we know is that given these kind of intervals, we should be very much comfortable. We should be making the DFT, and even if DFT is given and they are asking something about these things, then also you can tell about these things, right? So you should be comfortable with the start time and finish time now on. Okay, thank you so much.